All right, hi everyone. Welcome to CS50 Test Review. Goal of this afternoon is going to be an opportunity to talk about all of the topics that we've really covered in CS50 over the course of the first 8 weeks or so of the term, and to get an opportunity to ask questions in preparation for the test. So a couple of logistical notes before we get on to the actual content of what's going to be today's test review. Note that the test is going to be released later this evening at 7:30 p.m. It'll be released on the course website, so if you go to the course website, you'll see a link to the test there. You'll have until this Friday at 11:59 p.m. to turn in the test. There's no timer on the test. It's entirely self-paced, so you're welcome to take as much or as little time within that time frame to work on the test as you'd like, as long as you meet that final deadline of turning in the test by Friday the 8th at 11:59 p.m., and you'll do so by turning in the test via Gradescope, in much the same way that you've been turning in quizzes, where you'll upload a PDF of your responses, you'll choose which pages each of your answers to each of the questions corresponds to, and that will be how you'll turn in that test. A couple of rules about the honesty policy for the test. The test is entirely open book, which means you're allowed to reference any of the notes. You can go back and look at the lecture videos. You can look at the lecture notes, the slides, any of your own notes that you've taken. You're welcome to use any and all online resources that you'd like, so you're welcome to Google things, look things up for the purposes of the test. The only thing you cannot do is turn to other human resources. So you cannot turn to other students in the class or other people or your teaching fellows for questions. If you need to ask anything pertaining to the test, you should email the course heads, and if you email the course heads, we'll be able to respond to you, but that is just for like clarifying questions. You're expected to, for any of the content part of the test, you're expected to work on that on your own without turning to other human resources for help, but you're more than welcome to look things up online or reference any of the resources on the course website, whether that be lecture resources or otherwise. Questions about test logistics? Anything about how the test is going to work? Yeah. When can you expect results back after turning in the test? Usually we'll try and get the test graded within a couple of days, a week at most. Other questions about test logistics? Yes?
In our test, when we type it up, if we look up something on
If you look something up on Google, should you reference that in your test response? Yes. At the end of every question in the test will be a debriefing section, which will ask you which resources you used in order to answer the question. So any resources that you took advantage of, whether that's a website you looked up online or a lecture slide, just reference that in your response to that test question, just so we have that information as well. Other logistical questions about the test? Where? Oh, yes. Can you resubmit before the deadline? Yes, you're welcome to resubmit as many times as you'd like prior to the Friday midnight deadline. Yeah?
We can log in and out of the test across dates too, correct?
Yeah, can you log in and out of the test across dates? Absolutely. There's no limit on when during that range you can access the test. You can access it immediately Monday at 7:30. In fact, I'd encourage you to, as soon as possible, open up the test and at least read through the questions. And then you can continue to access it up until the deadline. Other logistical things? Yes, back there? There are no tutorials or sections or office hours during the test. Question up there? About how long should you expect the test to take you? In general, we say usually you'll probably be spending half an hour or a little more than half an hour per question. And you can look back at past year's tests and quizzes, and usually they're in the range of like 8 to 12 questions or so, somewhere in that range. All right, so a couple of ways in terms of preparation for the test, in terms of what to do. First and foremost, I would recommend reviewing any of the lecture resources. So that includes the lecture video, but also lecture notes, any of the source code examples that David demonstrated in lecture. All of that code is made available on the course website. So you can download that code or open it up in the sandbox or inside of CS50 IDE to read that code, understand it, experiment with it. And you can find the slides from all the videos as well from the lectures. All of the past year's tests and quizzes and the solutions to those tests and quizzes are also made available online. So that's another thing definitely worth looking at, because the style of the questions that are asked are generally similar in terms of the types of questions that we're asking, the types of things we're asking you to be thinking about. So past year's test quizzes and their solutions are available online too. And then I'd recommend taking a look at the problem sets. The problem set specifications are online, in addition to sample staff solutions that you can take a look at. And those are often helpful resources as well, just to give you a sense for the types of problems that you were asked to solve during CS50 so far, and therefore the types of things you might be thinking about over the course of the test. And then, of course, a great thing to do for the test preparation is what you're all doing here, attending the test review session. A really big goal of this is for it to be interactive. So certainly as we talk through all of the topics from week 0 all the way up until week 7, definitely feel free to flag any of us and raise your hand and ask questions, because we want this preparation session to be an opportunity for you to get your questions answered about whatever topics you might have questions about over the course of the curriculum that we've covered so far. In general, as we think about all the different weeks and the different topics we've talked about from weeks to weeks, there have been a number of different themes that have come up again and again. And one of the big things that we try to emphasize as we think about preparing for the test is thinking about those big themes and how it's connected to a lot of the different topics that we've covered over the course of the course so far. So the first of which is this idea of abstraction, the idea that once you've been able to understand the underlying details of something, you can begin to think about it at a higher level without needing to worry about those underlying details. So we saw that way back in Scratch Week when we introduced the idea of like functions and function blocks that abstract away the details within them, or the idea that once we understand that electricity can be on or off, we can build abstractions on top of that in the number system and other systems that we use for representing information. And then we saw that in more recent weeks with things like data structures, where data structures can often be thought of abstractions over lower level ideas, or even more modern programming languages like Python that introduce a lot of new abstractions, easier ways of implementing particular tasks in comparison to a language like C, where you didn't need to worry about a lot of those underlying details as you went about designing those programs. Algorithms are another big theme, thinking about if you're given a problem, what are the step-by-step instructions you might use in order to solve that problem, remembering that in that process you need to be very precise about telling the computer exactly what it is that you want the computer to be doing. You saw that this past Friday when we were doing the drawing example, where when you're trying to draw a figure on the board, you have to be very precise about the instructions you're using in order to do that. Representation is all about taking information and representing it inside the computer. So we saw a lot of different ways to do this for things like how do you represent text, but also how do you represent images, how do you represent more complex data, how do you store all of that inside of a computer, another theme that has come across a lot during the course. And then security, thinking about with any of the decisions we make, computers are vulnerable, and where are those vulnerabilities? We saw a couple of those vulnerabilities when we were talking about databases this past week, but we've seen other vulnerabilities when we consider things that might happen when things go wrong. And so we'll be talking about a couple of those today, and definitely feel free to ask about them as well. And then finally, a big theme has been trade-offs. The idea that anytime we get something in computer science, it often comes at a cost, that an algorithm that might be faster might come at the cost of using more memory, or an algorithm that might allow for certain operations might come at the cost of being a little bit slower. And so always thinking about with any of the decisions that we make in computer science, what the trade-offs there are. What are you getting for the choice that you're making, and what is the cost of the choice that you're making? And thinking about those trade-offs is another big theme that has come across time and time again over the course of CS50. So as we go through all the weeks of the class, we'll go through 1 week at a time, be thinking about those themes and how they connect to the topics in the course, because those will be some of the key takeaways from the class so far. Questions about any of the themes and the big ideas of the class before we go into, we'll start with week 0. All right, in that case, I'll turn things over to Emma.
Cool. All right, so we are going to start where you all started with Scratch and computational thinking in the very first or 0th week of the course. And we began with trying to think and act like computers in a certain way. So we learned about binary, which is a sequence of bits of 0s and 1s. So a bit can be a 0 or a 1. A sequence of 8 bits would be considered a byte. You can represent numbers from 0 to 255 in this way. Anybody know what this number is in binary? Some quick maths. It's really easy. If you guessed a number that we would put on the board, what would it be? 50, exactly. So here you can think of it sort of like a base 2 system. So we count typically with the base 10 system. You have your ones place, your tens place, your hundreds place, etc. And those are the sorts of operations that we are most familiar with in regular math. But in binary math, instead it's base 2. So the first place, the 2 to the 0th place can be either a 0 or a 1, representing quite literally a 0 or a 1, and so forth all the way up to 2 to the 7th for 8 bytes, for 8 bits to make 1 byte. Questions about binary? Great. so moving on from there, we have different representations of numbers, letters, things that we would want to store inside of our computer that we also want to be aware of how those are actually represented in memory itself. So in Caesar, you learned a lot about ASCII values, numeric representations of letters. We know that they're different for uppercase and lowercase letters, as you learned with your two lower and two upper functions coding in C later in the course. These numbers are also ultimately represented in binary. So this 65, which represents A, would be represented similar to the number 50 that we saw on the previous slide in binary when it's stored in your computer's memory. And moving forward, we thought about another way of representing something that we were interested in the filter problem set you had to deal with RGB triples. And so RGB values are numbers from 0 to 255, representing the amount of red, the amount of green, and the amount of blue in any given pixel. You know that you are able to manipulate those values individually. You're able to manipulate them as a series. And in your computer, they're stored as the values for the RGB numerically, just like ASCII, and then ultimately again in binary. Questions about representations of data? Yeah?
So it's the sum.
Yes, and so ultimately, the question is the sum of the RGB values is ultimately 255, and so yes, they go all the way up to that. Great. Other questions? Cool. So if we think about how then we use the letters individually and the numbers themselves, then we think about algorithms as a black box. And so in the first weeks, you were given access to things like getString and getInteger, where you were able to take a number from a user. You had some text right after it in order to get those values that you needed. Ultimately, those things, we didn't need to know how exactly they were working as long as we were using them properly. And so getString, you knew that you had to write get_string, you had to import the CS50 library, then say, ask for the name of a person in quotes right afterwards, and then they would type in a string to the computer, which your computer would then store in whichever variable you used there. The getString documentation and the actual code behind how it works is somewhere in the CS50 library. You could find it if you wanted it, but you didn't actually need to know how it was implementing such a thing in order to use it correctly. A lot of the power of computer science is reusing things that other people have written before, and so here we think about a lot of those sorts of things that you used in the first weeks of the course as black box algorithms. It takes an input, in this case it took a string from the user, and it gives you your desired output, a variable that holds that string. Questions about this black box structure? Cool. So, moving forward, then in Scratch, you were able to see visually what these sorts of things looked like. And so we learned about all sorts of tools that we have in computer science, such as functions. It takes something like this, the blue boxes in Scratch, and says move 10 steps. 10 is the input that you give the function. If you think of it sort of like your main function, it takes in any sort of variable. It usually returns void because it doesn't return anything directly. Here, this takes in an integer, 10, and it moves that direct number of steps. And so if we go to think about our previous slide, the input is 10, the output is the action of moving 10 steps. Variables are something distinctly that holds a value, and so it can hold a string, it can hold an integer, any number of things that you define. In this case, it sets my variable, which is the name of the variable, to be 28. That's the sort of tool that you would use many other times in C and Python and beyond. Conditions hold Boolean statements, and so you have ifs, elifs, else's don't hold anything because they're your ultimate final thing that's going to happen in your code. However, here, you know that your if-then conditions take in something called a Boolean expression. It says either, if A equals B, if A and B are both true, or operators, not operators. You would learn about the syntax directly of how you would use those things in C and in Python later. You know that they change a little bit, the double ampersand for and in C, the actual word and in Python. However, the idea is always the same. And you know that you are able to compare any number of things of the same type in this way. Loops, in a similar vein, represented in Scratch with these yellow blocks, it can repeat something a certain number of times. You learned about while loops, about do while loops, etc. And they are able to repeat actions any number of times that you define. And those were all of these sorts of things that you used and became familiar with in Scratch weeks. Any questions about those broad concepts? Cool. So then we'll move into week 1, where you guys actually the opportunity to start coding in the CS50 using C, your first programming language. And the very first program that you likely wrote was this one. You included standard.io.h, an int main void. You then wrote printf, hello world. Int main holds void because it doesn't directly return any values. The function isn't returning anything to be used anywhere later, but rather it's simply printing this message to you that you are now a computer scientist, you can print hello world, and this was where we started in one. Moving from here, we learned about all sorts of different types of data. So we know that a Boolean is something that returns true or false. Well, true or false are Boolean values. A character is a single letter. A double and a float are sort of related. A float is an integer, is a number that has a decimal point in it. And so it can be like 1.0 is a float, whereas 1 is an integer. You can represent things with more precision using floats than you could potentially using integers. A double is a float that has 16 bytes of memory rather than 8, or 8 bytes of memory rather than 4. And so that gives you even more ability to be even more precise with your calculations using a double rather than a float. Similarly with an int and long, an int is 4 bytes, a long is 8, so you can hold more information. A long is represented sometimes in different ways in different coding environments, but for the sake of the IDE, it would be 8 bytes. And then a string, which is an array of characters. You learned later a little bit more about what that means in terms of memory directly, but for the sake of week 1, we knew that strings were arrays of characters. Questions about data types? Yeah?
How many bytes is
4. Other questions? Cool. So, moving forward, once you had all of the tools to build whatever sorts of data you wanted, then you were able to use it. So here, we use functions like getString, those black box abstractions that are made available to you through the CS50 library, and you would write your variable name, string name, you declare it with the correct type, and then getString name. Then if I typed my name, Emma, in when prompted, then name would be a variable that held the string Emma, or the array of characters Emma. And then you could print using this syntax with the %s to hold a space for a string, essentially, and then pass in the variable name. For conditionals, they would look something like this. This is very familiar to you as well. You would write if x is less than y, print this, x is greater than y, else, etc. You know that if you have an ultimate condition, then you put it in an else without a Boolean expression, because anything else would fall under that condition automatically by not satisfying any of the previous ones. Questions about any of these things so far in C syntax? You're all experts, I know. So then if we move forward into loops, you would write for int I equals 0, I is less than 50, I++. How many times would that print something or do the action in the middle? 50, because that's how you set it. So the constraints in the middle say the number of times that you want something to happen, and that's every loop that you define has that sort of roadmap for how many times you want something to happen. Loops also can be like a while loop. So this one doesn't directly iterate over with I. You can use something like this if you don't actually need that value of I to influence the inputs that you're going through. We know that for a lot of our programs earlier, like if you think about moving through an image, you needed that I value in order to orient yourself within a picture, etc. But sometimes you just want to do an action a certain number of times. Then you could have a while loop or even a do while loop, which does something as long as another condition is true. Something else that you saw with maybe getting inputs from the user that match a certain number of constraints that you want to set. Questions about loops? Great. So then we learned how to define our own functions. And so you know that sometimes it's easier for both readability and repetition within your code in order to create functions of your own so that you can call them up in your main function and do the same thing over and over again without having to physically write repetitive code. We know that as programmers, we want to be as lazy as possible, and functions are a really great way to abstract out some of your logic and then apply it later in the future. So here we have a function for cough that takes in an integer n, and then for I is less than the integer n, we cough that number of times. And so you would be potentially in your main function, you would say something like get an integer from the user, integer n, and then cough that number of times. Maybe for every single person in this room, I wanted to give you all an opportunity to cough however many times you would wish, and then it would make a lot of sense to have this function separated so that I didn't have to repeat this code every time. I would just have to repeat getting an integer n from you individually and then running the cough function with integer n. Any questions about functions? Yeah.
Isn't there something you have to do if you like define it like at the end, but you have to put something in the beginning so that it knows where to reference the code that you define the function? Like
So I think the question is about structuring your code so that code, like if your main function is above, it understands that the function exists later. And so you can declare functions earlier on so that you can use them so you don't get like weird C syntax errors in order to use things in the order that you want them while they might be created later. Because this would probably be down lower in your code and your main function would be above it. What other questions do you have about functions? Sweet. So then you dealt in your quiz with floating point imprecision, and so we know that computer memory is complicated. It only gets more complicated as we get later in the course, but we knew even now when we were doing programs like cache that your computer memory doesn't have space to hold things exactly the way that they are. And so in a function like cache, you had to use the round function because when you divide 2 by 10, it does 0.2000000. That's all very correct. And then it sort of goes off the wire because if you think about the way that things are stored in memory, you might run into other blocks of things that aren't directly related to what you calculated. And so you always have to be careful about floating point imprecision in order to be sure that you apply the round function, etc., so that you're always getting back the results that you're looking for. And then a similar memory error that we saw in the Gandhi problem of one of the quizzes that you did is integer overflow. So here is a function that takes an integer I equals 1 and while true, which is essentially the C equivalent of a forever block in Scratch. You would printf I and then multiply I by 2. And so this would go on forever and ever and ever and ever and ever until the integer I that you defined originally can't hold it anymore. It would overflow back to the beginning. And so like in the Gandhi problem where you tried to subtract 2 from 0 and you ended up at the highest possible aggression rating, you have to be careful about where your values are headed and whether or not you have enough space to hold them there. Questions about integer overflow, floating point imprecision? Great. So that is all for week 1. That's when you were able to do your problem sets, the first ones in C, Mario, Hello, and Cache. And then we moved into week 2, where we talked about arrays and compiling. And so one of the first things we looked at was using Clang. Here we had this big bulky line where you took in the name of the program and the libraries that you had to import. All of that was difficult to remember and difficult to execute, and so then we gave you something called make, which made compiling a little bit easier. It did this whole process for you, where it took your original source code, say the program hello.c. It did pre-processing, which is the process of taking all of the things that you hashtag include, like standard IO or the CS50 library, and turns those, along with your initial source code, into assembly code. In compiling, then assembling assembles that assembly code essentially, and then links them all together. And so when it's turned into assembly code, the things that you included in standard IO and the CS50 library and your source code are all separate versions of all separate assembly code files. Linking puts them all together into one big binary file that your computer can read and execute correctly. And so this is the big scary process behind the make function, which simplified a lot of it for you. What questions do you have about compiling? Great. And so once we knew how to compile and run things and our code got a little bit more complex, there became a need to be able to debug it. When you're taking the test, it'll be important to note that there won't be office hours or tutorials as usual for other people to help find your bugs, and so it will ultimately be up to you to use the tools that we've given you and your own knowledge of how things are working in order to debug any coding aspects of the test itself. So you know that we have the tools Help 50 and Debug 50. Notes on how to use both of them are in the Notes tab of the Lecture 2 slides and presentation. And then you always know that you can use printf statements in order to see where you are at any given time. So if you know that something is messed up in a for loop, you can print every single variable you use in that for loop and usually tell by process of elimination and some clever printing where you're going wrong. Yeah? So Python is a little bit different in terms of compiling because you don't have, do you have a better answer for this?
Yeah, we'll talk about this a little more when we get to Python, which will be in a couple of slides. But in short, this is the process for C. Things look a little different for Python because Python is what we might call an interpreted language as opposed to a compiled language like C. And so the way that you run Python programs is a little bit different, but we'll get there.
It's a little fuzzier because you don't impact memory directly and things are a little bit more abstracted generally.
If it helps just to add one point there, in C, you'll notice that if you have some sort of syntax errors, you can't run the code because the compiler will catch those errors and break before your program actually executes. Whereas in Python, it just kind of executes line by line until there's some sort of error and then your program crashes. So you'll notice in Python files, you can have like a half-functioning program that does everything as expected and then crashes, whereas in C, you're not allowed to run it until you fix all the bugs.
Yeah.
Can you talk about how to use is it like Valgrind to do debugging as well?
We will talk about that when we do pointers and memory accessing. But that's another tool just like this that you would want to have in your back pocket for debugging on your own. Great. So moving on from debugging, we'll talk about arrays. So arrays are a super powerful data structure. You're able to store things in contiguous blocks of memory. And so if you want to be sure that things are right next to each other in a way that's easily accessible and you can use indexing in order to get to it all, then you would want to use an array. So here, if we write int value, then we get an actual integer called value. But if we write int values in brackets 5, then we get an array with 5 spaces for integers. And those would all be stored next to each other. We could do any number of things with them. So for example, I swear I didn't make these slides, Brian made them, I'm not that vain. But if we have a string name Emma, that we know that that's stored as an array of characters, EMMA, and then a null character. So even though my name is only 4 letters, it needs 5 spaces of memory. That automatically gets stored as an array. If I wanted to say array name bracket 5, then I could later put the string, the individual characters into it in order to get the same output. What questions do you have about arrays? Great. Ooh. So then we talked a lot about command line arguments because it's limiting to only be able to do, as we did in Mario, prompt the user for input once the code has compiled and started running and then act based on that. It's a lot more powerful if we're able to take things in directly and act upon them in our code itself. And so here we have Mario where you made Mario and then it compiled and then you use those arguments, and then we had a plurality where you passed in the names of the candidates themselves to the command line. And so here for plurality we know that we have int argc and string argv, which is the int argc is the number of arguments that you pass in including the name of the file itself, and argv is the array of the inputs to that file. And so here, what would argc be for this call to plurality? 4, and your array would be what? Ali, talk a little louder. Yes, and so then it's directly the things that you typed in, these 4 distinct strings of characters, and then the argc is the number of things that you typed in, which in this case would be 4. Great, so that's all for week 2. What questions do you have about command line arguments, arrays, anything from the past 2 weeks? Yes?
So in Python, if you see classifier directly array as well as character,
Mm-hmm.
Python is none, like how it's
I think you still consider it to be a null character, but it's not something that you access. So you wouldn't say like, this is none directly. Is that?
In short, in Python, with regards to the end of a string in Python, the idea of the string has been abstracted away a little bit, so you don't need to worry about how exactly that string is stored in memory. It's stored in a more complex way in Python than it is in C. So you don't need to worry about the null terminator when it comes to Python.
Yeah.
In Python, we were encountering
Yes. Mm-hmm. Cool. you had an array, if I put into that array of whatever the one of values 1, 2, 3, 4, 5, 5 would be the fourth technically index of that array. There wouldn't be a null character at the end. Sorry, the question was null characters are only for string arrays, character arrays. Yes? So that's correct. So there are 4 things stored in it, but with 0 indexing, yes. Actually, I'm pretty sure that argc counts from 1. Is that true?
Well, argc is the number of command line arguments. And so if there are 4 command line arguments and argc is 4, that means the individual arguments are stored at argv0, argv1, argv2, and argv3.
Similar to how if we create the integer array with space for 5 things, the 5th character would be at the 4th index.
And actually, this is great. This is something that you can test yourself as well when you're, in the IDE. You can just whip up a quick temp.c file and just write print what's argc, what's argv, or loop through the elements in argv, so that you can see for yourself and get this better intuition. Instead of having to try to memorize, you can actually just test for yourself and see it.
Yeah. They're stored as an array of characters, yes. And so then that's why in C programming, when you were taking in in integers in your array, then you had to apply the integer function to them. Great. So now Brian is going to talk to you about algorithms.
All right. So weeks 0, 1, 2 were really about building up the fundamentals of how to write programs in a programming language like C. So Emma talked about the building blocks of variables and conditions and loops. And now that we had all the in functions, and now that we have all this capability, the next step is how do we use that in order to solve problems. And so this was what week 3 was about. Week 3 was all about algorithms, trying to figure out how do we write code that is able to take these inputs and solve some sort of problem. In the problem set, you use this in order to implement a variety of different election algorithms. So a simple plurality election that counted up who has the most number of votes, but then looking at more sophisticated algorithms like a runoff election or the Tiedman election method that run a little more of a complex algorithm to try and figure out who the winner of an election is. But in lecture, we talked about a couple of strategies for how to represent information and then how to use that information inside of an algorithm. And the first key idea was the idea of a struct. And so here gave us the ability to create our own types, where Emma introduced the basic types that are already built into the C programming language, types like int and float and bool and char and long and double and those sorts of types. But if we needed to represent other types, like we wanted to represent a person, for example, as we saw in lecture, or in the problem set, you saw the representation of a candidate as a brand new type. In later problem sets, you saw a type for RGB triples, for a triple of red, green, and blue in order to store a pixel of information. None of those types are built into the C programming language, but that's OK because we can create our own types in order to represent that information. And so what we had here was the definition of a new type called person, where the way this syntax worked is we used the typedef keyword to say, let me have a new type with a particular name. What is that type? Well, the type is a structure or a struct, where you can think of a struct as a way of encompassing multiple different pieces or types of information into a single unit, into a single value. And so inside of a person, we're going to represent a person using 2 pieces of information. Every person has a string called name, and every person has a string called number that represents their phone number, for example. And recall that we used a string instead of an int because we wanted to be able to represent maybe hyphens or parentheses that might have been included inside of the phone number. So a string was a more reasonable choice for that. But we can choose exactly what we want to be inside of that structure. And so with RGB triples, inside of here we had separate fields, as we might call them, for some amount of red, some amount of green, some amount of blue. For candidates, we included a field in here for a number of votes. But in short, we could take whatever data we wanted to store, encompass it all together inside of a struct, and then call that new type a person, or whatever type we wanted. And that gave us the ability to more abstractly represent the idea of a person or a pixel somewhere inside of our program. Questions about creating your own types or structures? What questions do you have about that idea and how that worked? Yeah?
There was a change in syntax family needed to be struct to inside for example, a person pointer inside the person. How did that syntax change?
Oh, yeah, so good question. The question is, why did later on in future weeks we sometimes had to include the word struct somewhere inside of this definition? That was used when we needed for our data, for the type that we were creating, to be able to somehow reference itself. And so this came up in particular when we were talking about linked lists, where every linked list node contains a pointer to the next node in the linked list. Rodrigo will talk a little bit more about that later, but in short, when we need that recursive data structure, we need some way of referencing itself, and so we had to add an extra keyword here, but we'll see the syntax for that in just a bit too. But very good question. That was why we needed that. Other questions about types and structures of data? All right, so what did we use those structures of data for, and what was the purpose of it? Well, the first thing that we tried to do was solve a problem of being able to search for something inside of an array, for example. And so there were a number of different ways that we could search for something. But one way was to say, for example, if we have a big list of unsorted things, we could use linear search to say, like, start at the very first element in the array and then look one element at a time in order to try to find it. And can someone remind me, like, in running time, what was the big O of linear search? How efficient is linear search to search for something? Yeah. O of n, yeah, linear time to be able to search for something. Big O notation, recall, sort of encodes the idea of what is the worst case or the upper bound on how long it might take for this algorithm to run. And so in the case of linear search, it might take us, if we have n elements inside of the array that we're looking for, it might take us n steps in order to look through it. And so that was one method of searching for something. And what was a more efficient way to search for something inside of an array, if we stipulate, for example, that the array is sorted? Yeah. O of log n. And we used an algorithm for that called binary search. So binary search, another search algorithm, only works when the array is sorted. In linear search, it doesn't matter whether the array is sorted or not. But the idea of binary search is, all right, let's say we're looking for the number 50 inside of an array. We first say, all right, well, if there's nothing in the array, return false. We didn't find the number 50. If the middle item of the array is 50, well, then we found 50, so return true. And what are the only other possibilities? Well, if 50 is less than the middle item, then we need to search the left half, because if 50 is less than the middle item, then if 50 is inside of this array, it's got to be in the left half of the array. So we'll search the left half of the array. And otherwise, if 50 is greater than the middle item, then we'll search the right half in order to try and find that number. So this algorithm gives us a couple of different insights, but one of the big ideas is this idea of recursion, that we're solving a big problem by solving a smaller problem, that if 50 is less than the middle item, then we repeat this same algorithm just on the left half of the array. And we can keep repeating this process of solving a smaller and smaller and smaller problem until either there's nothing left in the array, in which case we return false, or the middle item is 50, in which case we found the number we're looking for, and in that case, we can just return true. And so if we compare the running times of these, this is where big O notation came in. This was the more mathematical side of week 3, thinking about, given an algorithm, how long is it going to take for that algorithm to run? And computer scientists use a notation called big O notation to represent that idea, where big O is all about the upper bound. In the worst case, or as an upper bound, how many steps will it take for the algorithm to run if there are n inputs? So in this case, if there are n items in the list, how long might it take to be able to search for a particular element? And we decided that, all right, for linear search, the running time is big O of n. If there are n elements in the list, it might take us n steps to be able to find the thing we're looking for, because in the worst case, it might be all the way at the end of the array. And we have to make our way through the whole array in order to be able to find it. And then, as someone mentioned, binary search is an improvement on that. In the worst case, it's log n. If we assume that if we're looking through the array, it's log n because we can cut the problem in half over and over again. We can look for the middle item, then choose one half, and then just keep looking to the next half of the items. And we don't need to look through every single value in the array. We can jump around a little bit in order to narrow our way down to the one value that we're looking for. So in this sense, O of log n is a faster algorithm in the worst case. Binary search was better, but of course it came at the cost of requiring that the list is sorted to begin with. Our array needs to be in sorted order in order for binary search to work. Otherwise, it's not going to work. So that's binary search, and also, as we introduced as part of binary search, big O notation, this notation we use for describing the runtime of algorithms, how long it takes for an algorithm to run. What questions do you have about that? Big O notation, algorithms, runtime. All right, we feel OK about that. In that case, related to big O notation was another notation. So while big O describes the upper bound on the running time of any algorithm, there was another notation we used called big omega, which was all about the lower bound on the runtime of an algorithm. So you can think of that as like, in the best case, how long might the algorithm take? And for linear search and binary search, what is the big omega? How long might it take in the best case, if we get lucky, for example? All right, I heard a couple people say it O of 1. In other words, constant time in the best case, meaning just a single step or some fixed constant number of steps. And why is that? Well, because we might just get lucky. And the first thing we look at might be the element that we're searching for. We might find 50 at the very beginning of the list in the case of linear search. We might find 50 at the exact midpoint of the list in the case of binary search. So depending on the algorithm, we might just get lucky, or depending on the array that we start with, we might get lucky and get the answer immediately. So often in algorithms, you'll find that the big omega, the lower bound on the running time of the algorithm, can be different than the big O of that algorithm, what it might take as an upper bound on time. And knowing the difference between those two and being able to think about that algorithm and deciding what is the big O of this algorithm, what is the big omega, that can often be a helpful way to frame an algorithm and think about the implications of its particular running time. Questions about runtime? Big O, big omega, how to think more abstractly about these runtimes. Another useful thing to remember is that when it comes to big O and big omega, we didn't really care about the constant factors or the smaller terms inside of the runtime. So it didn't matter if this was like n steps or 2n steps or 3n steps. The constant factor didn't really matter. What we cared about is what happens as n gets very, very big. And so we can throw away those constant terms, so to speak. And an algorithm that takes 3n steps or 4n steps, we can really just consider to be O of n steps. It's the n part that we care about, more so than what the individual constant factors happen to be. All right, so that was searching for something. And we stipulated that binary search only works if we have a sorted array first. And so one of the next questions that came up with algorithms was, how do we sort things? What are algorithms we can use for doing that? And we looked at least 3 different algorithms for being able to sort things. And the first of which was bubble sort here, represented in pseudocode, where the big idea of bubble sort is if we have a big array where the elements are unsorted, we look at the elements in that array 2 at a time, look at a pair of elements. And in a sorted array, the element on the left should always be less than or equal to the element on the right in any pair of elements. And so if we look at any pair of 2 elements and the element on the left is greater than the element on the right, then those 2 elements are out of order and we can swap them. And that's what bubble sort is all about. It's going through the entire array pair by pair by pair and making swaps whenever 2 elements are out of order. So the algorithm is, we're going to repeat this n-1 times. We'll come back to why n-1 in just a moment. But we're going to repeat this from 0 to n-2. So from the very first element in the array up until the second to last element in the array. Recall that if we have an array that has n elements, the first element is element 0. The last element is n-1. A little bit tricky because you have to start counting at 0. But for each element I, we're going to look at element I and I plus 1. And if they're out of order, we're going to swap them. And so we repeat that process again and again, making a swap, making a swap, making a swap. And at the end of this inner loop, the effect will be that whatever the largest element in the array is, it will bubble its way, so to speak, to the top of the array. Because we'll continue to make swaps until the biggest element gets to the rightmost position in the array. And there's one element that we have now sorted. And after that, we can go back and do the same thing again and again and again. And we only need to sort n-1 elements into their correct place, because if you have an array of n elements, and n-1 of them are in the right place, then the last element must also be in the right place, because there's nowhere else for it to be. And there was a visual demonstration of this shown in lecture where actual people were standing up here and they were switching places in order to figure out how to get into the right order. So that might be a helpful thing to go back and look at just to familiarize yourself with bubble sort. But if you recall from bubble sort, there was an optimization we could make to make it more efficient. Anyone remember what that optimization was? Yeah. Merge sort was an entirely different algorithm, but yes, it was more efficient, and we'll get to that in a moment. But with bubble sort specifically, there was a way we could make it more efficient. Yeah. Use a while loop. Yeah, and the idea here was we don't always need to repeat n-1 times, because as soon as we go through the elements pair by pair by pair, as soon as we go through all the elements and we don't swap anything, we can effectively stop running the algorithm. Because if we make it through the entire array and we never need to make any swaps, then we can just stipulate that the entire array must now be sorted. And so we were able to make this algorithm slightly more efficient by repeating until there were no more swaps left to make. So a slight optimization that might require running this algorithm fewer times. Questions about bubble sort and how that algorithm works? Yeah?
How can you tell that you're not swapping things?
How can you tell that you're not swapping things? Well, to do just a bit of a visual example, if we imagine we had 4 elements, let's say we had 3, and then 1, 2, and then 4. What we would do in bubble sort is we would start with these first 2, right? Say 3 and 1. Are they in order or out of order? Well, 3 is greater than 1, so these are out of order. So we would swap them. And so this would be 1 and then 3. Then we'd go to the next pair, 3 and 2. Well, these are out of order as well, so we can go ahead and swap those. And so now we have 2 and 3. Then we look at 3 and 4 and say, are these in order or out of order? They're in order, and so we don't need to do anything here. So that was one pass through the array. We went pair by pair by pair, making swaps. And then we might check this again. Say, all right, 1 and 2, have we made it? Do we need to switch anything? Well, no, we don't. They're good. 2 and 3, do we need to switch anything? No. 3 and 4, do we need to switch anything? No. And so we made an entire pass through the array, and we didn't need to switch anything. And so if you're keeping track of, did I actually have to switch anything? And the answer to that question is no. Then at the end of that, I can say, this array is now sorted. I don't need to go through it again and again and again, trying to see if there are more swaps to make, because if I went through this whole array and didn't make any swaps, then it must already be sorted. Otherwise, I would have had to make some swaps somewhere. Other questions about bubble sort? All right, so the next algorithm we took a look at was selection sort. This was a slightly different algorithm where instead of going pair by pair by pair and making swaps, the idea was if we have a whole array, let's figure out what belongs at the beginning of the array. And what belongs at the beginning of the array is the smallest element. So we went through the array, found the smallest element, moved it to the beginning. Then we did the same thing for the second element. Go through the rest of the array, find the smallest element, make that the second element in the array, and repeat the same process again and again, where every time we're just looking for what is the next smallest element to put into the array. And so that's the idea here. We're going through the array, find the smallest element between I and the last item, and then swap the smallest element with item I, where I goes from 0, again, all the way up to n minus 1. So that was 2 algorithms, bubble sort and selection sort, both of which achieve the same effect on the same input. They take an input of an array that might be unsorted, and the output is a sorted version of that same array. And anyone remember the runtime of these algorithms? What was the big O? How long did it take for bubble sort and selection sort to run? Yeah. N squared, exactly. So we'll talk about merge sort in a second. But in big O notation, n squared was our bubble sort and selection sort algorithms. And the way to remember that is you might look at what the loops are. How many times are each of the loops running? Well, in bubble sort, we're running this inner loop n minus 2 times, but in terms of big O, really only the n is going to matter here, so about n times. And how many times might this outer loop repeat? Well, we repeat until there are no more swaps. And in the worst case, we might need to do that n minus 1 times until there are no more swaps, because all of the elements might be out of order, or the list might be in reverse order, for example. And so if you look at the loops and think about for every loop, how many times is that loop going to run, that can give you a sense for the overall runtime of the algorithm. And whenever you have nested loops, the number of times that that code is going to run inside the innermost loop, you can think of as multiplying the number of times the outer loop is running by the number of times the inner loop is running. If you have an outer loop that runs 5 times and an inner loop that runs 4 times, the number of times that an inner block of code is going to run is going to be 20. Right? The outer loop is running 5 times, and for each of those iterations, the inner loop is going to run 4 times. So you can do the math and figure out how many times that code is going to run. So more abstractly, if you have an outer loop that runs n times and an inner loop that also runs about n times, then on the whole, your loop is going to run about n squared number of times for that innermost block of code. Questions about runtime for bubble sort or selection sort? All right, so next, as a couple people have alluded to now, is the idea of merge sort. This was our more efficient way of solving the problem, and this was a recursive way of trying to sort numbers. That if we have a big array of numbers, here's how we're going to sort them. We start with what we'll call a base case Anytime you have a recursive algorithm that repeats itself, that calls upon itself in order to solve a problem, you'll need some sort of base case, some stopping point to say, at some point I need to just know to not continue to call myself, otherwise the function is just going to run forever. We need some place to stop. And so in merge sort, the place to stop is once we get down to one item, one element in the list. And if there's only one element in the list, we can just return. We can say if there's only one thing in the list, then the array has to be sorted, because a list of size 1 is by definition sorted. There's no other order it could be in. But otherwise, if there are more elements in the list, here's the recursive algorithm. We start by sorting the left half, then we sort the right half, and once we have a sorted left and a sorted right, then it's not too difficult to merge those two sorted halves together by just figuring out one at a time which order the elements go in, because each half is already in sorted order. So that makes it pretty easy to combine them and merge them into a single sorted list. So this recursive algorithm is a type of algorithm that shows up a lot. Binary search was like this, where we said binary search the whole array by binary searching the left or binary searching the right. Merge sort now is like that too, where to merge sort a big array, we first say merge sort the left half of the array, then merge sort the right half of the array, and then combine those two results to get the answer that we want. And the runtime of that, if you recall, was more efficient than n squared. It was n log n, which is more efficient than n squared because log n is smaller than n, at least as n gets very big. So merge sort was our more efficient way of being able to sort numbers when they're inside of an array. Questions about any of these algorithms and why they have the runtimes that they do? Big O notation runtime, yeah. Yeah, so the runtime of merge sort in big O notation, in the worst case, is n times log n. And the reason why, if you recall, the way that we did this was, if I give myself an example here, and we said that we started with maybe 3, 1, 2, 6, 8, 5, 7, 4. The way we would sort a big array using merge sort is to start with like the left half, 3, 1, 2, 6. And how do you sort 3, 1, 2, 6? Well, we're going to do that by sorting the left half of that, 3 and 1. And how do you sort that? Well, you're going to sort the left half, which is just 3. And so what you end up building up is this kind of a tree-like structure where you're first going to take 1 and 3 and say, all right, with this list of 2 items, 3 and 1, how do you sort that? Well, it becomes 1 and 3. With 2 and 6, how do you sort that? Well, that's just 2 and 6. That's normal. 8 and 5, how do you sort that list of size 2? Well, that's going to be 5 and 8. 7 and 4, how do you sort that? That's going to be 4 and then 7. And so if you imagine that up here we had a big array, each of size 1, 3, 1, 2, 2, 6, 8, 5, 7, 4, you can think of the next step as being we took these individual arrays of size 1 and merged them into sorted arrays of size 2. 1 and 3 is now in order, 2 and 6 is now in order, 5 and 8 is in order, 4 and 7 is in order. And now we'll take those lists of size 2 and merge those together. How do you merge 1, 3, and 2, 6? Well, you get 1, and then 2, and then 3, and then 6. And then likewise here, 5, 8, 4, and 7, how do you merge those together? Well, the smallest one is 4, and then it's 5, and then it's 7, and then it's 8. And then finally, now we have 2 lists, each of size 4, and the last step is to merge them all together, and we get 1, 2, 3, 4, 5, 6, 7, 8. So this, generally speaking, is what merge sort looks like. We start with elements of size 1, merge them together to get elements of size 2, merge those together to get elements of lists of size 4, and then one final time in the case of an array that has 8 elements in it. And so if you think about how many steps this took, well, this is n elements. There are n sort of columns in this image. And how many times did we need to repeat this process? Well, we needed to repeat that process as many times as it took us to take a list, divide it in half, divide it in half, divide it in half until we got down to just 1. And we remember from way back in week 0 that the number of times we can do that, the number of times we can take an array, divide it in half again and again and again, is log n. And so we'll have to do this division log n times. And with each time, there are n elements that we have to manipulate or deal with. So log n times n gives us n log n. Yeah? How would you implement merge sort in C? It'll be similar in spirit to the pseudocode that we took a look at. So merge sort would probably be a function where that function took as input some list that you wanted to sort. And you would first call merge sort on the left half. Then you would call the merge sort function on the right half. And then you'd have to implement some logic to merge the sorted halves together, where that logic is probably going to involve taking each of those smaller lists and looking one element at a time, starting at the beginning, trying to figure out which one is smaller in order to merge those together. So it'll be similar to the pseudocode that you'll need to add some additional details in order to be a little more precise about it. Yeah? Will you need to be able to calculate big O and big omega? You should be able to, if you are like writing a function or you're describing some code or an algorithm to do something, you should be able to think about what it is that that algorithm is doing and think about what its runtime is ultimately going to be.
So like how do we calculate
Omega for merge sort. Anyone have a sense for what big omega for merge sort is? In the best case, how fast might this algorithm run? Yeah. N log n. Yeah. So the key idea here is that in the case of merge sort, there is no way to speed it up if the numbers are already sorted. If the numbers are already in sorted order or even in close to sorted order, we're still going to be repeating the same steps. Like merge sort doesn't care how close to sorted the array is. We're still dividing in half, dividing in half, dividing in half. We're still merging those sorted halves together. And that's going to take that same exact amount of time. So even in the big omega, in the best case, merge sort is still going to be big omega of n log n. Selection sort, meanwhile, still big omega of n squared. We're repeating that same process. The only one that does get more efficient is bubble sort. That becomes big omega of n in the best case as a lower bound, as opposed to n squared as an upper bound. And that was because of that optimization we made, where we said that in bubble sort, we can stop the algorithm after we reach a point where there are no more swaps left to go. And so maybe we just get lucky, and after the first run through the entire array, there's no more swaps left to make, and we're done. Yeah?
Wouldn't, if there's only one element that needs to be sorted, like there's just one number, wouldn't the best case then just be 1 for everything?
What happens if there's only one element? How do you analyze big O or big omega? In general, big O is all about what happens as the number of inputs gets bigger. So that's why we represent it using n, where n stands in for the number of inputs. So we're generally not concerned with the case of what if there's only one thing. We care about what happens as n gets big, and there become more and more elements that we have to deal with sorting. Yeah? What if there are an odd number of elements in merge sort? A very good question. In general, there you just break it up into approximately half. If there are 9 elements, you might do 5 and then 4. Question? Yes, go ahead. Back here. Oh, what sort am I using? Here, when I say sort the left half, sort the right half, I'm using merge sort. And so this seems a little bit weird that inside of the definition of merge sort, I'm using the merge sort algorithm. But it's OK because I'm using merge sort on a smaller array. That I start with an array of maybe 8 elements, and I call merge sort on an array of 4 elements. And as long as I always call merge sort on a smaller array, eventually I'll get down to this case, where there's only one element left, and then I'm done. So this is a recursive algorithm in the sense that it uses itself in order to solve a problem. Other question? Oh, so this is back to how exactly do we do this merging process? That if we have these two lists, how do we combine them? In general, if I have two lists that are already in sorted order, I know that the first element of the combined one must be either the first element of this list on the left or the first element of this list on the right. It's got to be 1 or 4, because everything later than it is bigger than the 1 or bigger than the 4. So I look at 1 and 4 and say, you know what, 1 is the smallest one, so that one goes first. And then I can say, all right, well, what comes after 1? 2. So it's got to be either the 2 or the 4 as the next thing. And you can go step by step like that, looking at the 2 smallest elements in each of the smaller arrays to figure out what the smallest element in the bigger array should be. And that's the general process. And there's some examples of that in the lecture slides as well. All right, with that, let's go ahead and move on to memory, talk a little bit about pointers, and go into a little more detail there.
Right. So you guys were all pretty comfortable with the explanations of binary and such from week 0 and week 1. And another way that we have of representing numbers is hexadecimal. So hexadecimal is essentially just another base system to represent numbers, whereas in binary we have base 2, where everything is either a 1 or a 0. And so you have the 0th place, the 0th place, the 1's place, and then like all the exponents of 2. So you have 2 to the 0, 2 to the 1, 2 squared, and so on and so forth. That's how you construct your numbers. With hexadecimal, you have a similar idea, except you're using base 16 instead of base 2. And so you're able to use 0 through 9 as themselves, and then the letters A through F represent the values 10 through 15. So this basically just gives you a different way of representing bigger numbers. And we generally use this in the context of, at least in this class, we used it in the context of pointer addresses. So if you'll recall pointers, especially if you used debug 50 or printed like the value of one of your pointers, you might have noticed that you got some sort of result that said like 0x, 1, 2, F3, whatever it may have been. That was hexadecimal notation. But all that you really need to worry about with hexadecimal is just understanding that this is another way of representing numbers that works similarly to binary, except the base is different. And instead of just using 1s and 0s, you can use any of these where 0 is 0 up through F being 15. So back to pointers, which I know is kind of like an intimidating concept, especially when you're learning it for the first time. And I agree, as a student, I also found it intimidating. But hopefully we can give you a little bit more intuition, and you can also check back the lectures for more intuition of this as well. One analogy that I like to use when I'm thinking about pointers and non-pointer values is the idea that memory in C is kind of like a neighborhood. And in a neighborhood, you might have apartments and houses and the like, and all of these have addresses. So you might live at, 123 Neighborhood Road or whatever. And so there's that concept of your house or apartment having an address. It's somewhere. And then you can go inside the house and look for things. So in this case, we have int n equals 50, where we can think of this built-in type of an integer as kind of just like a studio apartment where you walk in and there's just a space. You don't have multiple rooms or whatever. So you walk into the studio apartment, that's this space in memory that we call n, and there's a 50 that lives there. Whereas in this case, down below, where we're declaring a pointer called p, we have that the integer star p, which is the notation that we use when we're declaring a pointer, we're initializing it to be the address of n, where if you recall, the ampersand symbol is what we use to get to the actual address of like a variable, for example, this integer n, where if we just refer to n by itself, we get its value. So if we refer to n, it's like we're looking inside the studio apartment and seeing the 50. Whereas if we refer to ampersand n, we just care about what's the address of that studio apartment. Where is it? Where is it in the neighborhood? And so in this case right here, we have integer n is set to 50, and the pointer p is set to the address of n. So if you look at the value of p later on, I guess we can draw this a little bit. And is it this one? No, this one. If we look at the value of p now, we get that this value is actually going to be the address of n, where initially we declared star p as ampersand n. So when we actually refer to p, we get this address, where the address of n might be something like 0x, oh, I overwrote this a little bit. The address of n might look something like 0x, like 1, 2, 3, for example, and so on and so forth. Let's just say 1, 2. So that's actually the address of p. Whereas if we then dereference p using the asterisk, that's a star. Using the asterisk mechanic that we have, this is actually going inside of the address where P is holding, the address 1, 2. It's going to that address, checking inside the apartment, and then it sees that there's a value of 50. So let's actually go back to this slide now. That is to say then that when you're dereferencing a pointer, which is when you're referring to it with the little asterisk, that means that you're actually going to the address of that pointer and checking inside to see what value is there. Whereas when you're just referring to the pointer itself by its variable name, like P, it's just giving you the actual address. Before I go further, are there questions about this? Are people confused about addresses versus the actual values that it contains? Yeah, I see a hand back here.
Wait, so if I wanted to use P to give me 50, I would do star P after I declared it, or just P?
Yes. So here, you can also think about it as the fact that we are setting or in this case, we're actually declaring it, so it's a little bit misleading. But after we declare it, when we're actually wanting to use P, if we say star P, that gives you the value contained at the address to which P refers. So that means if you just do P, it gives you the address of N, where N might live in 0x123. And then if you do star P, it goes to 0x123, checks what's there, and it finds a 50. Does that answer your question? OK. So let's look at this. In this case, P lives somewhere in memory. When you declare a pointer, just like when you declare a variable, you're essentially like taking up some space in your computer where this reference to the pointer is going to exist, because pointers don't magically not take up space. This pointer actually lives at some position in memory itself, and the value that is contained at that position in memory is the address of a different variable. So in this case, P lives at some address. We don't give it a name, but what it contains is the address of N, where here's N. N contains the value 50, but it lives at this address. So when you actually get the value of P, you're getting its own address, whereas when you're getting the value of star P, you're getting the address of N. When you're getting the value of N, you get 50, and when you get ampersand N, which is how you refer to the actual address of a non-pointer variable, is how you get the actual address. And I'm kind of using pointer and address a little bit interchangeably here, but that just goes to show that you can think of pointers as essentially just containing addresses. So that's a little bit of a visual there. In the context of strings, to make it a little bit more concrete, we said to you at the beginning of the course that strings were just array of characters, and we kind of left it at that. And then later on, we kind of took off the training wheels, and you saw that a string is essentially just a pointer, where here we define the string called S that stores Emma. A string is just a pointer that holds the address of the first character of the string. So if the string is Emma, and we store it in a pointer or in a string variable called S, what's at S really is the value of the address of E. So that then you can go to that address and you get E back. And if you want to refer to the string at position 0, you just have to go to this address and you see that it's an E. If you want to go to the position or the index 1 of the string S, since strings are just arrays of characters and each character only takes 1 byte, then underneath the hood, you know that you only have to add 1 to the value of this address to get the value of the next block of memory, since strings are contiguous memory. And so that's how strings are essentially operating, where you just have a reference to the first character, and then you can just add some values to it to get the address of whichever index in the string that you want to go. I don't want to lose anybody here, so definitely raise your hands, wave at me if this is confusing. Raise up your hands if this is making sense. OK, cool. And was there a question here?
Oh, yes. So if it were 8 equals 8%, and it would actually store the actual address, like 0x123, if you have 8 asterisk E equals ampersand N, then it would store the actual value of the count.
Yeah, you have to be careful because the question is, what's the difference between saying int p equals %n or int star p equals %n? And you just have to be careful, and this is why people get confused. One of the reasons why people get confused with pointers is that when you're declaring a pointer, you have to use the asterisk. You have to say int star p to tell the computer that this is going to be a pointer. So you would want to say int star p equals %n, because if you just said int p, then you're telling the computer, give me a normal integer. And then that integer would just contain like the value of that address, because it's in hexadecimal, so it's a number. And so when you're actually declaring the pointer, you do want to use this int star p. But once the pointer's been declared, from then on, once you reference star p, that means you're dereferencing it, and which means you're going inside the house and checking what's there and seeing what value, if it's a 50, or if this is a Boolean pointer, if it's true or false, or whatever type it is. And if you just refer to p after it's been initialized, that means you want the actual address. OK. So, oh, question. Where? Yep.
If you wanted to change the value of, say, n, would you use n or would you use star p to change that?
That's a great question. The question is, now if we want to change the value of n, do we do so by changing like now n equals 17 or star p equals 17? The answer there is that you can do both, because the pointer is essentially a reference to that location in memory. So if you can follow that and then access that location in memory through the pointer and change the value, then since this is, n and p and star p are referring to the same place in memory, if you change the value there, then any references to that place in memory are going to be changed. And you can also see this if you have two pointers and you point them at the same address and you change the value of that address with one pointer, you can then see that it's changed if you access it through the other pointer. Because just keep in mind that everything that you're doing lives in an actual place in your computer. And since pointers are just references to that address, then they allow you to go there and change whatever's there. And then anything else that refers to that location, we'll see that the value's been changed. Great question. Another one here. So clearing up pointer versus array versus pointer to an array. So you can think of a pointer and an array as essentially the same thing, where they both refer to the address of the first element, or an array refers to the address of its first element as a pointer. So if I say like char array of size whatever, and I set that to Emma, or I ask for memory dynamically to store the size of the string Emma, and I set int star p to be that, then I can access all the characters in the string essentially the same way. If I have a pointer to an array, then that's essentially like having a two-dimensional array almost, where you can have, like if you think of a board, you have one index for like rows and one index for columns. And since arrays and pointers are kind of the same thing, then if you have a pointer to an array, you end up with a two-dimensional array, essentially. OK, these are all great questions. I love them. Keep them coming. So I referred to asking the computer dynamically for memory. And so we've seen examples of this, especially in Speller, when we were dealing with porting over a file containing words to our own data structure that we then called the dictionary. And the way that malloc played into it was that this is a function that asks the computer for some dynamic memory. And then at the end of the execution of your program, you need to make sure that any memory that you've mallocked or asked for dynamically is also freed, so that your program isn't then leaking memory, which is where Valgrind comes into play. And I'm going to use this visual to talk about it a little bit, where you can think of, so again, the motif here is that everything that you do on your computer is essentially like there's somewhere in your computer that's representing that. And so your actual code itself, after it's been compiled and assembled and linked and whatnot, you end up with machine code, and so that lives somewhere in memory. You can think of it as living here. Then any space that your global variables and such are taking also take up some space in memory, and let's say that lives here. And then everything else in your program also takes some space in memory. Where we use the stack, we refer to the stack as the place in memory where all local variables live. So if you have like a function, you call it f, and then in your f function, you declare some variables like x, y, z. X, y, and z are all going to live in the stack. As is your function, f is also going to live in the stack. The things that live in the heap are things that you explicitly ask the computer for. So if you're asking the computer via malloc or calloc or those similar functions, hey, give me 4 bytes to store an integer, or give me 1 byte to store a character, then whatever memory that you're asking for is coming out of the heap, which is then, like, if some people in Speller may have run into like some sort of memory overflow error or segmentation faults or the like, especially with these overflow issues might arise from you're asking for memory and you're asking for memory, but you're also taking up memory in the stack, and so eventually the heap and the stack like collide and you're out of memory and you don't have anything else. So this is just how we represent memory in C. And you use Valgrind as the question from before. Valgrind is a program that you can run on your actual code, on the execution of your program to then let you know if you're leaking memory, where leaking memory means that you've asked for memory dynamically on the heap, but you didn't give it back, and you haven't freed it. So if you don't free that memory, then it can't be used for something else if you're asking for memory, unless you reset it yourself manually. So see if I ask, malloc, and I'm not going to use the exact syntax here, but if I malloc 4 bytes, and at some spot in the computer's memory, like say these are 4 bytes right here, I've asked for this, and now if I ever ask for other memory, I'm not going to be given this because I've already been given it. So if I keep asking for memory and asking for memory, I'm eventually going to keep being given memory and given memory and given memory. And if I don't ever give it back, there's going to reach a point where if I keep asking for memory, the computer's going to be like, hey, I gave you all I got. There's nothing else. We have a problem. Whereas if you're actually freeing memory once you're done using it, then that same piece of memory can then be given back to you if you ask for memory again. And that's essentially what Valgrind does, is just checks for whether you're not giving back memory that you've asked for. And that's what we call leaking memory. And this is kind of like a nice visual for how you can think about where things live when you declare them, or when you ask for them with malloc versus when you just declare them naturally as local variables in your functions, or when you declare functions themselves. That was kind of like a brief overview about pointers and memory, but I know that there's usually a lot of questions about this, so definitely let me know what other questions are there. Yes?
You have to create, after you say malloc, you have to write like free memory after each malloc, or can you just have free memory?
The question is, and correct me if I misheard you, whether after you ask for malloc, you have to like free it right after? Not technically right after. So if you recall in the Speller example, you malloced memory, or you asked for memory via malloc to store your dictionary words, and then you didn't free it until later on after you unloaded the dictionary. Just as long as before the program terminates, you have freed any memory that you've asked for, then you're good. You don't have to like free it right after, or it's good practice too. Once you in your program know that you're done referring to a piece of memory you've asked for, to just free it. But you can technically get away with just freeing things right before the program terminates. There's another question back here as well. No? We're all good? Yes? Right, so the question is, when we said int star p equals ampersand n, can we then use p and ampersand n interchangeably? And I think the answer is yes, right? Yeah. The only thing is that then you, just for readability, I guess it doesn't matter. As long as you're being consistent, it's better to just use one thing to refer to something instead of mixing and matching, because then people have to say, wait, what is this again? The safe answer is just use p, since you've already stored $n in a variable. But technically, they're the same, so you can use them interchangeably. Okie dokie. I'm about to talk about data structures, so stop me now if you have any final questions. So I have to squint because the lights are like awesome. All right, one more question over here.
Could you explain one more time the intuition of why a pointer is like an array?
Yeah, so again, the intuition of why a pointer is like an array. This is just because of the way arrays are implemented underneath the hood, where the way that arrays work is they are essentially pointers to the first element of the array itself. So declaring a pointer is just kind of like explicitly doing that without worrying about any like syntactic sugar or whatever. Where syntactic sugar is just like syntax that does something in a little bit of a nicer way than having to do it explicitly. Yeah? Right, so with files, when you're opening a file, you get a pointer to that file itself. And the question is, what's the difference between fget and fread? I would have to check the documentation, but I think fget gives you 1 byte at a time, correct? Do you want to talk about
C, for example, there's a number of different functions for reading and writing from files. And if you check out man.cs50.io, which is CS50's programmer's manual, there's some descriptions of all of these. But fgetC, for example, is just going to read to you 1 character at a time. So you call fgetC, you'll get 1 character. You call fgetC again, you'll get the next character. fread is generally used if you're reading some number of bytes at a time. And so in the case of recover, for example, you wrote a program to read from a memory card, and the way you likely did that was not by reading 1 byte, 1 byte, 1 byte, but you probably read in like 512 byte blocks, where you would read 1 block at a time, then read the next block. And so fread rather can read a certain number of blocks from a file and read it into somewhere inside of your computer's memory.
Okay, let's talk about data structures because pointers are still relevant here. Who knows what this is? Raise of hands. Linked list, I'm hearing murmurings, yeah, linked lists. And this kind of goes back to the idea of what I was saying, like memories like a neighborhood, where now instead of like when you say int n equals 50, let's say the n is like a studio. Now when you're getting the linked lists for which we use structs, where you can have multiple types under one name, we can talk about 1-bedroom apartments or 2-bedroom or whatever if we want to extend the analogy, where maybe in the living room is the actual thing that you're looking for. Maybe in the living room is the integer. And then in the bedroom, there's like a little clue, like a scavenger hunt. Here's an address of another house. And so if you follow the address of the other house and you go check it out, you see in the living room, oh, here's another integer. Here's the integer 2. And then in that bedroom, there's another scavenger hint that says, hey, check out this address. You're going to find something there. You check out that address, and you see in the living room, there's a 3. And then in the bedroom, you don't have any clues. You don't know where to go from here. And this is null, which means that we're not pointing to anything else. This is the end of the linked list. And pictorially, we represent it using arrows so that we don't have to worry about hexadecimal notation and addresses and whatever. It's just overall kind of nicer. But you can just keep it in the back of your mind that this is actually what it is, right? It's just one portion of the struct contains, an integer, whatever value you're looking for. It doesn't have to be an integer, but for example. And then another portion of the struct contains a pointer to another struct of the same type that's going to contain an integer, and a pointer to another struct of the same type, and so on. This is essentially what linked lists are. Why are linked lists good? Why would we bother using a linked list rather than an array, for example? Don't be shy. Yeah? Perfect, yes. With a linked list, you have dynamic memory allocation. Let's say that right now, your last element here, you decide that you don't want this to be the end of your list. You want to add something else. Well, you can just use malloc, get a little bit more memory, and set an address here on this element to point to that new struct that you've asked for. Whereas with an array, when you declare an array, you have to tell the compiler how many elements in that array do you want off the top, like up front. And then if you want more elements in that array later on, you're just going to have to ask for a new array, and it's a whole ordeal. So with linked lists, you can just continually grow it and use exactly as much memory as you need or you want. Why might you use an array over a linked list? Maybe someone on this side? Yeah? Exactly. Arrays have random access, because when you ask for an array and you tell it, hey, I want an array of 40 elements, and if it's an integer array, then that means that you get 40 times, let's say you have an array of characters and you ask for 10, you get 10 bytes. So the 10 bytes are contiguous. And so you know that since the blocks of memory are all right next to each other, you can access through pointer arithmetic the last element or the middle element or so on and so forth just by adding however many bytes you need to get to that index. Whereas with the linked lists, since you're just asking dynamically for memory, this memory can come from anywhere in the heap. It's not going to be right next to each other. Maybe this house is in one corner of the neighborhood, and this one is all the way at the other end. So you just have to kind of like, if you're looking for a specific element in your linked list, you just have to keep following the breadcrumbs until you reach the actual house that contains the element that you're looking for. So there's this element of trade-offs here. And here's the question about the answer to the question about the syntax. The reason why we have struct node here in this definition of like a node, where you'll recall a node contains just a number and then a pointer to the next node, is that if we want to refer to the node, we need to be able to call it something. And in the previous example of a struct, you notice that we just had type def struct and then the fields, but there was no name. So there wasn't any way to reference to a struct. And so here, when we give it the name here, type def struct node, now we can say, oh, this type is struct node. So struct node pointer next. And then as before, you also put the name here just for syntax's sake. But yeah, that's just so that you have a reference to the actual name of the struct so that you can refer to itself recursively. Otherwise, if it has no name, there's no way to refer to it. OK, so we've seen arrays, we've seen linked lists. Here's a binary search tree, which in a way is really just a linked list that's been taken to the next level. You can imagine, and let me define this real quick. A binary search tree is a tree that has, where each node has maximally 2 children, and then each child to the left of a node has to be less than or equal to, depending on the implementation. It can be strictly less than or equal to. Let's just say strictly less than. Each child to the left of each node is going to be strictly less than the value of that node, or the value at each child. So here you see we have 4, 2, 1. And you can imagine a trivial case where, let's say we have the numbers 10 through 1, and they're all just kind of like less than the previous one. So you just end up with a linked list, right? Because 10, 9, 8, and so on and so forth. So really, these are kind of like linked lists, except we try to, there's other types of, there's like the height balanced binary search trees that enforce this kind of like construct where you have more of a actually balanced tree instead of just one trivial linked list. But in theory, let's imagine binary search trees that are balanced on both sides, where the height to the left is at most 1 more or less than the height to the right of the tree. What might these be good for? Spoiler in the name, right? Just searching. Binary search is going to be very easy in this tree because it's inherently sorted. You know that if you're at any particular node, anything to its left is going to be less than that value, and anything to the right is going to be greater than that value. So this is amazing if you're looking for Mike Smith in the phone book, or what have you. Or if you're interested in questions such as, what are, given some structure of information, you're looking at, or you're asking a question like, how many things are less than some specific value, or what things specifically are less than some specific value. Then you can go to that specific value and just grab everything to its left. So there's plenty of applications for binary search trees, but primarily, yeah, for searching, they're great. They'll run in log n time like we've discussed with binary search. We've also seen other data structures like hash tables. Can anyone explain how a hash table works? You can look at the diagram, yeah? See a hand back there? Yeah, yeah, it's an array of linked lists, essentially. And you can think of it really as an array of struct pointers, essentially, where it's a pointer to a struct where we've defined the struct to also contain a pointer to the next one and so forth. But at its simplest level, an array of linked lists is the way to go. And recall that especially in the examples with Speller, when we were looking at dictionaries, the way that we decided where a particular entry might go in a hash table is by hashing the value of the element and then producing an index. So if we remember the simplistic hash function that we came up with for let's say dictionary, if you look at the first character of a word, it tells you, in our alphabet from 0 to 25, ignoring case, it'll tell you where on an array of size 26 to put a particular word. So Alice might go at index 0, Bob might go at index 1, and so on and so forth, up until Zacharias would go at position 25 in the array. And then any time that you have another word that begins with the same character that goes at the same position in the array, you can kind of get over this collision by making a linked list so that you can then go to position 25 and access Zacharias and access whatever other Z names that you have there. This is not necessarily a great hash function, this looking at the first character. Can anybody tell me why? Why might an array of size 25 not be the best? Yeah.
Because like theoretically, you could have everyone's name start with the letter C, and then the whole point of that hash table is not really useful.
Yeah, precisely. Like, what if you're looking at a set of names that all begin with the same character? Then suddenly you have one entry in the array that has 26 nodes, and then all the other ones are empty. You're not really using your memory like very efficiently. Or just what if you're looking at a huge number or a huge list of names, and even if they're spread out fairly evenly across the different indices of the array, there's just ends up being like a huge linked list for each one. So this is the nice thing about hash tables, is that you can kind of like structure or ask for as much memory as you think you're going to need to avoid collision. So you can, instead of using a simplistic hash function that just looks at the first character and gives you back a number between 0 and 25, use a more complex hash function that does some magic underneath the hood to a string and then outputs some number between whatever 0 or like 20,000. And then suddenly you can have an array of size 20,000 to store all these different names in, such that you can theoretically have constant time lookup, assuming that you don't have a lot of collisions based on how many different buckets each name can fall into. The trade-off there is then that you're just taking up way more space to save on time. And there's like different types of hash tables that will address these types of things. But I'm not going to go into it for the sake of what we've seen so far. In terms of other data structures, we've seen tries for retrieval. And these are essentially kind of like an inverse of a hash table, one might say, where it's a tree where each node contains an array of pointers to other nodes that contain arrays to pointers to other nodes. And in addition, each node also contains a flag that tells you, for example, in the case of dictionaries and words, whether the current node is the end of a word. So a trie might look like a node where you have an array A through Z or whatever alphabet you're using. And if you store or are looking for the word hello, you would, let's say you're looking for it, so it's already here, you would check the index of the character H in the array, see if there's an H there, or true or false, or whatever, however you want to do this trie. Let's say that if a word is in the trie, you just set the index of the array at that node to be true. So right here where the H is, that would be true. And then you go to the next node and you see if the E in that array is set to true. And then you go to the next node and you see if the L is set to true. And at each point you're checking, is the end of word flag set to true if you're just checking if that's a word. Up until you get to hello, where you see that H, E, L, L, and O are all in the trie, and in addition, at this node that contains the O, there's the flag that says this is the end of a word. So then you can confirm whether hello is in the trie. And in theory, the nice thing about tries is that even though they take up a huge amount of space, they give you what's essentially constant time lookup, especially for English words, where the longest word that we have is, I think, like 45 characters long. And so you have at most big O of 45, which is really big O of 1, lookup for words. You just have like an incredible amount of space that you're taking up. So there's these trade-offs again. We've also talked about abstract data structures like dictionaries. In the context of Python, if you'll recall, a dictionary, you can access it it's a data structure that contains key value pairs. So if you have a dictionary D, if you're using it to store students, you might have like a student's name, you might have student's HUID, you might have a student's house, and if you access D at key name, it'll give you back like Emma or Brian or Rodrigo. If you access at HUID, it'll give you back whatever value stored there. The nice thing about abstract data structures, such as queues and stacks as well, is that since they're abstract, that means that you can implement them with, like, say, linked lists or with arrays or whatever actual tangible data structures that we have. So example, like a queue, which is just a data structure where the first thing is the first thing in is the first thing out. It's in the name, right? Like a queue if you're waiting in line for a store, or if you own a restaurant and you support online orders. In theory, you want the people that order first to get their food first. So you might store them in a queue where the two kind of like standout properties of it is that it has an enqueue function and a dequeue function, where enqueue stores or inserts an element into the queue and dequeue takes it out. And so in theory, with a queue, you have if this is your queue, you insert elements here, and then they end up coming out here. Whereas with a stack, you insert elements here at the top, and then they also come out from the top, where a stack is kind of like a stack of trays. You insert elements, and they start getting kind of buried under all the new insertions, and then when you get something out, you just take the one at the top. Whereas with a queue, the first thing that goes in, you also want it to be the first thing that goes out. And so queues we refer to as first in, first out, FIFO, and stacks are last in, first out, LIFO, or LIFO, however you want to pronounce it. But yeah, the main takeaway with these abstract data types are that you can actually construct them with whatever data types that are tangible that you want. And if you're curious, you can actually implement a queue using two stacks, and you can implement a stack using two queues, and there's all kinds of fun stuff that you can do there. But this is the main overview of data structures, and I want to stop here to ask what questions there are before I turn things over to Brian to talk about week 6. Yeah?
What are the two words that correlate with enqueue and dequeue?
Oh, right. What are the two words that correspond to enqueue and dequeue for stacks? So for stacks, you have push and you have pop, where push means that you're pushing to the stack or you're inserting into it, and pop means that you're taking out of the stack, where it's, I don't know, push and pop just sounds like you push it and then you pop it off the top. I don't know why. And enqueue and dequeue are the corresponding ones for queues. Any other questions? You guys see anything I don't see? Okay. Without further ado, let me turn things over to Brian to talk about week 6.
All right, 2 weeks left in the class to talk about. So up until week 5, everything was all about C, this lower level language where there was no magic. If you wanted a data structure, you needed to build it for yourself. Week 6, we now introduce Python, a higher level language where more is given to you. Python is an interpreted language where instead of compiling the code first into assembly and then into machine code, we run a program called an interpreter that is just reading our Python file line by line and executing those instructions. And those instructions ultimately look a little bit different than the instructions looked like in C, but there are a lot of similarities. So in order to print something out, we would call a function, just as we did in C. In this case, the function is called print, and the argument is put in parentheses. So hello world is what we would call the argument to that function or the input to that function. If we store the result of a function like getString inside of a variable called answer, we can again print out the value of a variable using print. And the way we do that in this case was using what we called an f string, a special formatted type of string, where we could use these curly braces here to mean plug in the value of a variable inside of the string at this position in the string. So answer is a variable, and when we put answer inside of those curly braces, we mean take the value of answer and plug that into the string, and then print out the result, so that we end up saying hello to Emma or hello to whoever typed in their name into the program. We saw a couple of other types of syntax. Here's how you do a variable in Python. I can just say counter equals 0, name a variable equals a particular value. Values in Python have types, so counter in this case is an int, but unlike in C where you needed to specify when you declared a variable what the type of that variable was, I needed to say in C int counter equals 0. In Python, Python is able to infer the types for you. If you say counter equals 0, well, Python knows that 0 is an integer, so it may as well just treat the variable counter as an integer. So it's not that the types don't exist. The types do exist, and you can still use those types incorrectly. It's just that Python figures out for you what the types are without you needing to specify what those types are. Increasing a variable counter equals counter plus 1, very similar to C, just no semicolons in any of Python. And whereas in C we would enclose blocks of code, like blocks of code inside of a condition or inside of a function or inside of a loop using a pair of curly braces, in Python we do it by having a colon, and then everything inside of the block of code is indented. So the indentation is mandatory in Python, where here we're saying if x is less than y, then execute any of the code that is indented, printing x is less than y. And as soon as we stop indenting, that code is outside of the if condition, so to speak. Hopefully this is familiar. We can also have else conditions, so if x is less than y, and then else, where again we end else with a colon, and then followed by indented all of the information inside of the else block. And we can have elif, E-L-I-F, instead of else if, as it was in C, to add additional branches there, as we have different conditions, each of which might do something a little bit different. Loops in Python, very similar to loops in C, where again we can use the while keyword to repeat some block of code as long as some condition is true. If the condition is literally the word true, that means this is going to continue to execute forever. So this will print hello world again and again and again. But that true could be replaced by any Boolean expression, checking if two things are equal to each other, checking if one thing and something else is true, or one thing or something else is true. So a lot of those same ideas that we saw in C, again, apply in Python as well. And then loops in Python might look a little something like this. For I in range 3, range 3 is the way in Python of getting basically a sequence of 3 elements, 0, 1, and 2. So this is going to repeat 3 times, 0, 1, 2, just printing out cough. So a little bit more succinct than writing the same idea in C. You don't need the int I equals 0, I is less than 3, I plus plus syntax that you probably wrote a number of times over the course of the last 7 weeks or so. It's a little more succinct in the world of Python. And then in terms of the types that we have, or question, yeah. So what do you do if you want to increase I by 2 every time instead of by 1? Couple ways you could do that. One is that, though it wasn't shown in lecture, range can actually take additional arguments. So you could specify not only like count 3 times, but you could say like count from this number to that number, counting in 2s or counting by 3s. So you can add additional arguments to make that work. And you can take a look at Python's documentation for exactly what the order of those arguments are. Alternatively, you could use something like a while loop, where you just have a variable called I, and then inside of the while loop you say I equals I plus 2 to increase I by 2 every time you run the loop. Other questions about Python syntax that we've taken a look at so far? All right, so data types in Python. We saw some data types that existed in C, so Boolean values, floating values, integer values, and string values. These are all types that are built into Python. But Python also has some types that we didn't have access to in C directly that Python will just give to us. And these are often types that we'll use for representing sequences of values. So a range, for example, is for a sequence of numbers, where, for example, range 3 gave us a sequence 0, 1, 2, so we could easily loop over a range of possible numbers. A list is kind of like an array in C. It's a sequence of values that you can mutate, that you can change. And so unlike an array in C, I can add things to the list, I can remove things out of the list, but this is a mutable sequence. I can add to it, remove from it, change elements inside of that sequence. Unlike a tuple or a tuple, which is a sequence of immutable values for things that aren't going to change. So Python draws a distinction. If you have a sequence of values and you know that sequence of values is not going to change, you're not going to need to add anything to it or remove anything or modify any of the values, you can use a tuple type instead in order to represent that data as well. And then finally, a couple of other types that you've probably seen over the course of the past couple weeks. A dict, short for a dictionary, is a collection of key value pairs, where a key value pair is any time I want to map one piece of information to some other piece of information. So in a phone book, for example, I might want to map people's names to their phone numbers. Or in an actual dictionary, I might want to map words onto their definitions. Or in the case of the DNA problem that you worked on for problem set 6, you might have mapped DNA sequences to the number of times they repeated inside of a person's DNA. So anytime we have this generic idea of wanting to map one type of value onto another type of value, a dictionary can often be helpful for that. And then finally, we took a look at sets, which are just for collections of unique values. And so in lecture, David demonstrated how you could write a spell checker by using a set in order to store all of those words, just a collection of values for storing information. Each of these different data types have different operations you can do on them. They run in different runtimes, and all of that information is on Python's documentation. And so definitely a useful resource to take a look at either now or during the test if it comes up is taking a look at Python's documentation for these things to get a sense for how it is that these data structures work and what their runtime ultimately is like. Questions about Python and that syntax? All right, so, and then in the context of Python, we were also able to talk about the idea of regular expressions. So we could use a library in Python, the regular expression library, to look for particular sequences of characters. So if I wanted to check to see if someone had typed in yes, or maybe we wanted to just accept y or yes, we could use a combination of these regular expression characters to be able to express that idea. And so a question mark, for example, means that something is optional. I could include it, or I don't necessarily need to include it. So if I want to check, if I'm having someone type in some input, and I want to check, like, did they type in y or did they type in yes, and I want to accept both of them, then one thing that I could do is say that, all right, well, I want them to definitely type in y, but the es is optional, for example. And so I might, in parentheses, say es, and then a question mark. And this was the way in lecture we said, here's how you can represent the idea of either y or yes. The y needs to be there, but the es is followed by a question mark, which means the es is optional. And so you'll often see regular expressions in the context of checking to see whether or not an input is valid. If you've ever had to go to a forum and type in an email address and it rejects it because it's not a valid email address, odds are it's because there's some regular expression that's checking, like, does this actually look like an email address? Are there characters followed by an @ symbol followed by other characters? So you can use regular expressions to do that type of input validation as well. So questions about Python or regular expressions or any of the features of the language that were talked about in week 6. All right, one last week to talk about in terms of content of the course. So we looked at C, then we looked at Python, and then this past week we looked at SQL, a language used for interacting with databases. And there were a number of things we wanted to do with databases. We wanted to be able to create a table, which you can think of as like a spreadsheet table, just something with rows and columns for storing data. And then there were operations that we wanted to perform on that table in order to add data to it, modify that data, update that data in other ways. And so the first thing we needed to know how to do was how to create a new table. And to do that, we used a create table query, where the query looked like this: create table, followed by the name of the table, in this case movies, as was the case in the problem set that you just completed. And then we specify what are the different columns of that table. What are the fields or properties of every movie that I want to store, along with what type of information do they represent. So here inside of the movies table, every movie has an ID, which is an integer, just so I can uniquely reference every movie. Every movie has a title, which is of type text. It's just some text-based information. And I can add constraints to particular fields. I can say the title is going to be text, but it's not null. I can't have an empty title where I have no title. Every movie must have a title, and not null enforces that constraint, that every movie needs to have a title. Every movie has a year, just some numeric value representing what year the movie was released. And then down here I specified that the ID column is the primary key. And the primary key just means this is the main way that I'm going to reference a movie, and it is going to be a unique way to reference a movie. That, yeah, maybe two movies were released in the same year, maybe two movies have the same title, but no two movies will have the same ID. The ID is a unique way of identifying one particular movie, and so we're calling it the primary key, the main way via which I can uniquely reference a single movie. What questions do we have about this create table query, how we create a table for these movies?
Why would you make ID integer? Why don't you put not null on that since you need it to uniquely identify each movie?
Why do I not put ID integer not null? I certainly could add a not null constraint just to enforce that as well. Yes, you could do that. In general, often what you'll do with an integer ID field is you'll add a property to it called auto increment, which means the ID will automatically increase to the next value. This was the case in the houses problem that you worked on. The table we gave you had an automatically incrementing ID field, so you didn't need to worry about the ID. And there, that way, the database will enforce the property of always giving a new ID to every new item we add. All right, so now that we have this table, how do we add data to that table? To do that, here was the query we ran. We ran an insert query to insert data into the table. And the way that query worked is we said insert into what table? The movies table. And which columns am I going to specify values for come next? So in parentheses, title, comma, year, because I'm about to insert a value for a title and then a value for the year. What values am I inserting? Well, I'm inserting Toy Story and then 1995. So the title of a movie and then a year. And importantly, the order of these values needs to be in the same order as the order of the columns that I specify. So here I'm saying Toy Story is the title, 1995 is the year, and that is the row that I would like to insert into my movies table. Yeah? Yeah, so what happens if, for example, there's a field that's unique, like an ID field, or maybe there's some other unique field that I've specified that the database needs to make it unique, and I try and insert something into that database where the uniqueness constraint fails? You can actually try this, but most databases will reject the insert. It will not let you insert something into the database if it violates a constraint, like a uniqueness constraint. Likewise, if I try and insert something into something where it says not null, I might get a database error that says that if I didn't specify a value for the field, it's not going to let me insert it into the database. And so that's why we add those constraints, so that the database makes sure that we don't use it incorrectly. All right, how do you update data after you've inserted it into the table? Let's imagine that Toy Story's rating has changed on IMDb's website, and we need to somehow update this in order to reflect it. We say update followed by the name of the table we want to update, in this case, movies. What do we want to change? Set rating equal to 8.2, for example, whatever its new rating is. And if I just had this first line, update movies, set rating equals to 8.2, the effect of that would be that every movie in the database would now get a rating of 8.2. Here I'm assuming the movies table has a rating column, which wasn't in there before, but let's just imagine for now. In order to specify which movie I wanted to apply to, I might say where title equals Toy Story, to constrain myself down to only a particular title. And for this particular movie, I want to set the rating equal to a certain number. Deleting from a table follows a similar rule. If I want to delete all the movies that are the worst movies in the database that have a rating of 0, I can say delete from movies where rating equals 0, for example, and that will achieve that effect. Was there a question here? What do you want to do if you want to change more than one thing in update? Whatever this where clause returns, that is the number of rows that it is going to apply the update to. So I could update multiple different, if there are multiple movies called Toy Story, if I wanted to update all of the movies with a rating above a particular number, or all the movies released in 2008, you could do that just by specifying a more general where query, and that would be able to achieve that effect. Oh, if you wanted to change multiple fields, yeah, you can. I'm pretty sure you can include multiple comma-separated ideas there. I forget the exact syntax, but it's along those lines. All right, so what came up next was how you deal with like multiple tables. If I had multiple tables that I wanted to join together somehow, And the way I can do that here is to say, I want to select maybe let's imagine now that instead of having a single table that has movies and ratings, as we saw in the problem set, you separated that data out into multiple tables, a movies table and a ratings table. And the way to join that information together was to say, select the columns I want, the title of the movie and the rating, from the movies table. But I need to now join it with some other table to be able to access the information I want. So I can join it with the ratings table. And then when I join two tables together, I need to tell SQL how to join those tables together. So I can say the ID column of the movies table is equal to the movie ID column of the ratings table. Those two columns are how these two tables line up. It's how the data relates to one another. And so I can join tables like this in order to combine two tables together to be able to query across multiple different tables. And there are a couple of ways that I can query for information across multiple tables. One way is using that join syntax to join multiple tables together. Another thing I can use are nested queries, where I take a SQL query and put it inside of another query. So if I wanted to figure out all the people who starred in Toy Story, for example, one thing I might do is first just select the ID for movies where title equals Toy Story. In other words, what is Toy Story's ID? And then for that particular movie ID, let's get all the people that starred in it. So select all of the person IDs from the stars table, where the movie ID is whatever Toy Story's ID is. So those bottom two lines are going to tell me what Toy Story's movie ID is. And then that first line uses Toy Story's movie ID and looks in the stars table to find all of the people who starred in that movie. So you can take a SQL query, put it inside of another query, and repeat that process, nesting queries inside of each other. In this case, I'm assuming that select ID from movies is only going to give me back a single ID. But if I wanted the stars of all the Toy Story movies, not just the first one, I might do something like this. Change the equal sign to a like. I don't want to just look for Toy Story, but any Toy Story % sign, where % sign is a wildcard, meaning look for any movie title that begins with the word Toy Story. And then here I changed where movie ID equals to where movie ID in, to mean if the movie ID is in any of the IDs of movies where the title begins with the word Toy Story, then I want to query for it there as well. Questions about that syntax? Yeah.
Just to press. So the difference between A and equals, like first column, equals just looks for one value, where maybe it's for all of the values, or like equals find the first value.
Yeah, equal sign generally used for the first or the only value where there's one value that I'm looking for. In generally when I'm dealing with a sequence of values and I want to check for membership in that sequence. Then finally, just to wrap up SQL, a couple of threats or concerns you might want to be aware of. The first of which is race conditions, which can happen if multiple people are trying to do something with the database at the same time. So if, for example, two people are trying to like an Instagram post at the same time, what might happen? Well, if the code isn't written quite carefully enough, you might end up with situations where two different programs are trying to update some value in a database at the same time, and they conflict with one another in order to get potentially dangerous results. So something to be mindful of there as well. And then a particular danger has to do with what's called SQL injection, which is what happens if you're not careful and you just literally plug in values into a SQL query. If you're just plugging in input into a SQL query, you allow for the possibility that an adversary could plug in dangerous SQL code into your query in order to get you to run code you're not intending to run on top of a database. So for example, if someone logged in, but in the login name, they added like a end quotation mark and a dash dash, where dash dash in SQL introduces a comment in SQL, so it ignores the rest of a query. Then you might imagine that a login system that is checking someone's username and password, if you literally just plug in the dash dash, it's going to comment out everything after the query, which means it's going to ignore checking the password, which means if the person who's designing the system has not done so securely, they might end up allowing someone to log into an account, even if they haven't provided the correct password, by nature of using SQL injection, this security vulnerability that we can defend against by making sure to escape our input. And that's one thing that the SQL library does for us. So questions about these threats or vulnerabilities in SQL? Yeah, question?
Sorry, this is going back to joins and nested queries.
Yeah.
There were some times during the problem set where I was trying to use join and it wouldn't work and I would have to use a nested query. Why is that so?
So joins and nested queries can be used for similar things. There are just some situations that will often lend themselves better towards one or the other, just in terms of how you might logically think about it. And it's going to vary a little bit from problem to problem. But yeah, it's a good question. Yeah? Group by is another piece of syntax we didn't quite look at just now, but it's a way of taking all things that share the same value and collectively grouping them together into a single entry. So if you group things by a person ID, you'll get all of those person IDs grouped together into a single row. All right, so we'll go ahead and wrap up here. The test, again, is going to be released at 7:30 later this evening. You'll have until Friday in order to work on it. We'll stick around for a little bit to answer questions if you do have them, but best of luck with the upcoming test.